In this video, we're going to learn about comparing a single mean to a hypothesized mean using a z-score or a t-score. So you can begin with your full MRSA data of 208, remove the missing and create a subsample of 30. See the creating a subsample video if you haven't already done that. I'm going to do a quick distribution on the original percent resistant so that we can take a look at how our subsample compares. This is the same subsample that is listed in the notes, and it's my simply just 30 rows that were selected randomly, no missings. And I'm going to do an analyze distribution on my percent resistant here. And I can see my sample of 30 versus my sample of 177. You'll notice that the 177 has a little bit more of a normal looking distribution, and then the subsample of 30 is almost bimodal. Because our sample size is so small, we only have 2 rows that are between 50 and 55, or 2 observations, whereas here there are 24 rows in the original data set that fell in between 50 and 55. So there's a number of things that we need to look at with our data before we consider testing. And what you might want to begin with is taking a look at the normal quantile plots. And we'll do this for both the full sample and for the subsample. In both instances, it's this drop-down menu here, and we can ask for a normal quantile plot. We'll do the same thing here on our sample, normal quantile plot. And you can look at the difference here. On the right side in the full distribution, we can see that the line is much straighter. The dots follow the red straight line much more closely, and there's very little bit of wavering. Whereas on the left, on the sample size of 30, we have a little bit more of a departure from that center straight line. But that's okay because all of our dots have stayed between the bounds. So you can think of this a little bit like driving, where you want to stay underneath the speed limit and in between the lines. And if you think of the speed limit as the straight and narrow and the lines being your lane on the road, normality is the straight and narrow and in between the lines. On the right, we have much more normal data looking, and on the left, we have wider confidence bounds because we have a smaller sample, and we can see a little bit more wiggle in our data. But we do know that our underlying sample is normal, and in addition to that, we've drawn a subsample of 30, which meets our central limit theorem. In this case, we can feel comfortable with our means being normally distributed. And remember, it is the means that we are testing. We're not testing the distribution for normality of our sample. We're testing the means using normal assumptions. And so all we really need to know is that our underlying population looks relatively normal and our sample is large enough to cling to the central limit theorem, and that normality of our means will hold. So I'm going to close out or move over our overall sample here so that we can focus on testing. Testing a mean is very similar to testing a single proportion. In your drop-down box of your 30 sample distribution, click on Test Mean. JMP will display a box that has your options for all of your testing. The default testing of the mean is 0. We do not want to test the mean of 0. We want to test the mean equal to our population mean over here shown on the right side. And we want to test it at 47.450282. If we want to do a z-test, then we're going to enter in our standard deviation. If we want to do a non-parametric test, we will click this box. But for now, let's simply do a z-test, which means we are going to pretend that we know our standard deviation, and that standard deviation comes from, again, our distribution of 177. And so that's 10.794212. Now, it is important to note that we're showing this for demonstration. It is incredibly rare that you know the standard deviation of your sample. You will almost always be using your observed standard deviation and doing a t-test. This is for sample comparison only and just for an example for you, but very rarely in practice are you doing a z-test. You're almost always doing a t-test. So for here, to get the z-test, we've entered in our population mean from our full distribution. We've entered in our population standard deviation from our full distribution, and we'll press OK. And I'm going to close my quantiles and my summary statistics here so that we can see what comes up from the test statistic or the test results. You can see we've done a z-test here. JMP will summarize for you the hypothesized value that you put in. It's rounded it to 4 decimal places, but it will not round it to those 4 decimal places testing. Here's our actual estimate. So remember, if we look at the summary statistics here, our mean is 48.923333, and our mean here is 48.9233. We have a sample of 30, so our degrees of freedom are 29. We had 30 observations. We're using 1 degree of freedom to estimate our mean. We estimated our mean here. So our degrees of freedom are 29. We have our known standard deviation down here, which is the 10.7942. Here's our observed standard deviation. But because we've done a z-test, this is the standard deviation that's being used. Notice it says sigma. So our known sigma, not our S. We're using the known sigma on a z-test. JMP will then calculate the test statistic for you. This is identical to the one in the notes. And then you can choose your p-value. Because our null hypothesis here is our observed value of 48.9 different from our observed value of 47.5, then we are going to be reporting the two-sided p-value. That's this top one. It's the two-sided p-value because it's looking at both sides or the absolute value. So it's looking to the left and the right of our standard normal curve. If our alternative hypothesis was greater than, we would use this p-value. If our alternative hypothesis was less than, we would use this p-value. In our case here, the p-value is 0.4548. That is greater than our alpha of 0.05. That means we will fail to reject our null hypothesis of equality. We will conclude that our observed mean of 48.9 is not statistically significantly different from our hypothesized mean of 47.5. Our conclusion in words is that our sample of observed data is not statistically significantly different from the underlying population mean of 47.5% of tested positive MRSA samples being antibiotic resistant. That's the z-test. If we don't know the standard deviation, which is almost always the case, we want to run a t-test. Just again, ask JMP to test the mean. Here comes our test mean box again. Again, I'm going to enter in the population mean of 47.450282. I am going to leave this box blank. Remember, right here it tells me t-test. Enter it if you want a z rather than t. So I'm not going to enter anything, and I'm simply going to press OK. And then JMP gives me my t-test results, which are down here on the bottom. You can see again actually that our testing results are very similar to what we saw above. The first 3 rows are identical. 47.405, 47.405, 48,923, 48,923, same degrees of freedom. What's different from our z-test and our t-test is that here we gave it the standard deviation as sigma. Down here, we're using our observed standard deviation. So there's no sigma value given in the t-test, and that's because we don't know the standard deviation. What we're going to use is our observed standard deviation from this sample, and that's our 10.2487. JUMP will then calculate the t-test for you, and you can again see here that we have three options. These three options align with our alternative hypotheses. I know they align with the alternative because there are no equals signs here. Remember, the equal sign is always in the null. Here we don't have those, so these are our alternative hypotheses. We know that our null is equal to and our alternative is not equal to, which means we're going to report this p-value of 0.4375. JUMP has also given you a diagram here of what the distribution of the t looks like, and you can see our values here of our mean. This blue line right here is our hypothesized mean. This is our acceptance region. This is our rejection region, would be over here. You can see our value is the red line here. We observed a 48.9. It's being compared to this, and this gives us our p-values. So it's very similar to the p from z calculator, but we're no longer doing a z, we're doing a t. The more blue or teal shaded area that you see, the less likely you are to have a small p-value, and in this case, we have a large p-value of 0.4375. And we will reject, or excuse me, we will fail to reject the null hypothesis of equality, which means we are concluding with a t-test that our observed estimate of 48.9% antibiotic resistant samples is not statistically significantly different from the assumed 47.5% antibiotic resistant samples. So that is how you test a mean that you are assuming to be normally distributed. So remember, here from our normal quantile plot, it appears to be okay with normality, as well as the fact that we have a sample size of 30. So we can test with a z-test if we know the sigma. Most cases we don't, so we can test a t-test, and we will get our p-values, and from there we will take over with the writing of our results for the results of this test. In the next video, we will look at a non-normal distribution and how to test that.